Hello COIL, welcome to module 2 of our COIL journey. In this module we are going to cover the foundation systems for structural and construction systems for houses in Honduras. Well, the main objective of the footing is to be the kind of foot of your building or your house, and is the part of the structure in charge to transmit the whole weight of the structure to the soil. Making a kind of comparison between a structure and a human body, the foundation systems will be like the foot, and as you can see, the area of the foot is greater than the ankle. So the greater the area, the lower the pressure on the soil. Or as another example, when you lay down in a nail bed, your skin does not get punched because all your weight is distributed along a big area. So that's the main idea with the footing systems. We usually have some loads that comes from the columns, as you saw in the introductory video, and this load must be transmitted to the soil through the footing system. So the wiser method to do this is through a wider area, because in this way the pressure applied to the soil will be lower. Why do we need the pressure on the soil to be lower? And it's because all the soils have some microscopic behavior based on mineralogic properties and the grain size properties. Those macroscopic behavior can be described as the bearing capacity of the soil and the shear capacity of the soil. Remember that these two main characteristics or features of the soil is given by the mineralogic composition, and talking about mineralogic composition, it refers to the kind of minerals that make the grains that compose the soil, because the soil is composed by many particles arranged next to each other, but these particles, which are technically called grain size, may vary, and all this package is the soil. So remember, the grain size and the mineralogic composition of the soil govern the macroscopic behavior of the soil that can be described for practical purposes for the bearing capacity and shear capacity. As you can see in this illustration, we have a isolated footing which is receiving a distributed load, and this load is transmitted to the medium or to the soil, and the soil responds with an stress pattern. Such a stress pattern is composed by normal stresses and shear stress. The bearing capacity is related with the normal stresses the soil can withstand in this zone, and the shear capacity is related with this kind of failure surface that a soil below a footing system can develop. To determine these two important properties that are the bearing capacity and the shear capacity, we have to do a geotechnical prospection. For most simple projects, the bearing capacity is enough, and for some more sophisticated projects, we need to perform a test, especially to determine the shear capacity of that soil. Okay, the way to determine the bearing capacity of the soil is through a standard penetration test. The standard penetration test, in simple words, is a correlation between the number of hits made with a standardized weight takes to drill or settle this axis by 1 feet, which is approximately 32 centimeters by 1 feet on the ground. In the next slide you can see a video of a standard penetration test, and this test is ruled by the standard ASTM D1586. These photos are the standard penetration test made for the house we are using as example in this COIL project. For that house in particular, just visualize this is the land. We have 8.5 meters in front and 25 meters in this direction, and we did 3 geotechnical prospections, one in the back, one in the middle, and one in the front of the land. So now you are going to see the standard penetration test. This standard penetration test is from 2013, and I apologize because the phones in that time didn't have automatic rotation of the screen, so the video it's laid down, but I think you will get the idea. Just let me play this. So this is the axis, the main axis that is being drilled in the ground by hitting with this standardized weight. I don't know if drill is the correct word here, but I think with the video you got the point, because the drilling involves a rotational movement. Just by making a comparison, there is another standard penetration test in which the method for determining the bearing capacity is not with the free fall of a weight, it is with a rotationary machine, and that specifically it's drilling, and it's another kind of standard penetration test. And that one it's mainly used for rocky soils. Okay, according to the Honduras standard, which in turn is based on the Universal Building Code or Unified Building Code from 1994, the minimum information a geotechnical report must contain is the following features. The first one is the soil classification according to SUCS. SUCS, it's the acronym of, let me remember, Sistema Unificado de Clasificación de Suelos. That in English it will be Unified System for Classification of Soils. It was developed in the USA. The second information that geotechnical report must contain is the level of the water table. If that does not exist, the geotechnical report should say there were not a water table found in this geotech prospection. The third one is the recommendations for the footing design. Since the geotechnical prospection is performed or at least led by a geotechnical engineer, he has the expertise to recommend the builder or the designer a particularly Footing system, just for citing something, it will be a isolated footing or maybe a continuous footing. The third one, and the most important for us, is the soil bearing capacity. That is the correlation or the measurement between the number of hits made by the standard weight and the amount of penetration of that axis that you saw on the video. And the third and the last one, which is also very important, is the expected elastic settlements. This is how much you can expect the soil can compact in the elastic way. And as you can see in this report, we have the sample 1, the sample 2, and the sample 3. The sample 1 goes from 0 to 1 meter, the sample 2 from 1 to 2 meters of depth, and the sample 3 from 2 to 3 meters of depth. And as you can see here, when it said capacidad soportante en campo, that in English, that it's the soil bearing capacity in situ, they are giving us this value. This value is expressed in kilograms per square centimeter, which means, for example, that at a depth of between 1 to 2 meters, the soil bearing capacity in this strata can be expected to be a force of 4.37 kilograms per centimeter square. That's the bearing capacity. And just as example, you can see in this slide the Unified Soil Classification System, which stands for SUCS, o Sistema Unificado de Clasificación de Suelos. This table and these letters gives us the mineralogic composition of the soil. Or let me do a correction, it's not the mineralogic composition, it's the classification of the soil based on the grain size particle. Just for giving a brief on this kind of classification, according to the particle size of the soils, we can classify it with, for example, gravel, sand, clay, and between sand and clay we have limos, and there is a letter, a sign for this kind of, for every kind of classification system. And when we are talking about gravel, think gravel itself. Those are big stones, usually between 2 inches and just saying 3/4 of an inch. And below 5 millimeters, we have the sand. And think about the sand on a beach. And below that grain size, we have, for example, clay. And when we talk about clay, just think about how, for example, dust. Some dust are very, very small. And this classification system, the SUCS, is based on the grain size of the particles. As you can see, this grain size, which is given in the SUCS soil classification, this is the table of example, and on the right hand you can see an example of the soil classification given by a geotechnical report. For this geotechnical report in specific, they gave us the soil classification of the strata every roughly 50 centimeters for the first two, and then every 1 meter for the rest one. And you can see GM and you can find GM on this table. You can see MH and you can find MH in this table. MH it's for inorganic limos soils with some sand and elastic limos. And for every strata of the soil, the geotechnical report gives us the soil classification. Now it's time to see the most common construction systems for footing systems in Honduras, especially for building houses. And there are two main: concrete footings and masonry footings. In the classification of concrete footings, we have isolated footings and continuous footings. These two here are examples of isolated footings. As you can see, it's a kind of path on the soil that is in charge to transmit the load carried by the column and transmit that force to the soil and distribute it in a wider area. And to connect all the isolated footings, we have these beams or foundation beams that, especially in Honduras, we call it, for this foundation beam, solera. This one is the same as this one and is the footing systems for the house we are using as an example. And in a couple of minutes you are going to see how it behaves mechanically in the macroscopic level. This one on the right have some foundation beams thinner than these ones, and that affects the behavior of the footing system as a whole. The another footing system is the continuous footing, and it seems like this. For the continuous footing, a cross section of that footing will be this one or will be this one. You can see in this section we have the footing by itself. It could be concrete from the depth till the level we desire, or it could be a concrete pad, then we gain height by making masonry blocks. These masonry blocks are filled with concrete, and in each partition of the block we have a rebar steel, and at the bottom of the pad we have also rebar steel. In a couple of minutes I'm going to explain you why this rebar steel is there. This is the most common one in Honduras, as well as this one. We could also have a continuous footing made with masonry stone, and it consists of stone which are glued together using mortar. Mortar is a combination of Portland cement, sand and water. So we dig in the ground for having the area for our footing, then we start putting stone, and for gluing each stone we use the mortar. Then when we achieve our final height over the masonry footing, we have the foundation beam, and then from the foundation beam we start to build our walls. This one is this one, and you can see in a following video how this structural system for footings behave on soil. And this one, a cross section of this is this one, and a cross section of this one might be this one, but more specifically just visualize this one. Now in the following slides you are going to see some videos for the construction process of the isolated footings of the house we are using as an example. Look, the isolated footings, then we have the rebar steel that goes from the footings, and then we start the columns.
Que según donde se encuentre lo firma.
Before putting the rebar steel in the bottom and the rebar steel of the column, we usually put a small layer of gravel just to be sure that the concrete we are going to use in the footing will not be in direct contact with the soil, because that can contaminate the concrete. And this is the formwork of the columns after having poured the concrete pad of the isolated foundation. And just before we go, I will explain you why we need rebar reinforced in the bottom of the footings. Every footing, let me see if I can clean some of this. It's transmitting the loads of the columns to the soil. So, by the third law of Newton, remember, every action has a reaction, and the reaction of the soil, it's a force, and the resultant of this distribution is equally in magnitude of this force. So the concrete pad is submitted to flexion. We have this and we have this, and the flexion will cause this section tries to do this one, and the concrete, it's a very good material to withstand compression forces but not tension forces. When we cause some flexion in this pad in this way, compressive stresses are formed from the neutral axis to top, and tension forces are formed from neutral axis to the bottom. So this region is prone to have tension stresses. These tension stresses will cause some little cracks, and to control these little cracks and to give a strength to our footing systems, we need to put a rebar in this direction. This rebar is the one that you see here, and we also need some longitudinal rebar that goes in this direction. This longitudinal rebar have the same function as the rebar in a beam. For example, imagine just this section is this one, and by having some loads that comes from the columns, we have this kind of beam over elastic supports, and we will have a kind of behavior like this. So we need rebar in this direction, in the longitudinal direction, due to the same reason we are using, or I previously explained with this example. And that's because the footings all have rebar steel. And the same principle applies to the isolated footings. And that's the reason, because if we see an isolated footing from top, we are going to see a kind of rebar steel mat like this. As you can see in this picture. For you to understand deflection, please consider this piece of foam. If I apply forces and generate this shape, this effect is flexion. Using the same foam, when I apply forces in this direction, or I say yes, you can see, this effect is compression. If I apply forces pulling out, this effect is tension. And if I apply two moments in this direction, this effect is torsion. Okay, I'm going to show you now the behavior of 4 different types of footing systems for the same house we are using as an example. Just to remind you, we are using this 2-story house, which is composed by the structural system as a whole, and now we are going to analyze the footing system. The footing system for this house specifically is composed of isolated footings with some beams, which are tensor beams, which in Spanish are called solera, and the function of this kind of beam is to connect the different isolated footings for our house. This is the footing system. It was selected for the house, and in the following minutes of the video I'm going to show you some pictures of the footings as built. But before showing you that, I want to explain you the behavior of different footing systems for the same house. So one might observe here that the such beams that connects the different isolated footings serves for a double purpose. One is to give some kind of support for some walls that goes on top of every beam described here. As you can see, as I move the cursor, you can see how some walls are located just on top of such beams. But there are some beams that have a function just to connect two isolated footings, but it doesn't contain any wall on top like this one, for example. In our 3D printed model, you can see it here. And for example, this is the frontal part of the house. This 3D printed model is showing you just until here. And please pay attention that the kind of footings we are using in this part of the structure is an eccentric footing. We are using this kind of footing system because next to this just because we have a neighborhood just here, so we cannot put a concentrically centered footing like this one, because if we do so, we are passing or using some portion of our neighbor. So we have to use this kind of footings in the line that marks the division between our land and the land of the neighbor. So saying this is the frontal part of the house, this is the garage, this is the part for the a kind of sidewalk that goes into this frontal part, and here is the main door. Here we have a wall over there, and this one here is our last footing, that it will be this one. Now observe how this system behaves when I apply some loads on it. The loads comes from the columns from these columns, and such loads are the resultant of some weight distribution in the story deck, and such weight distribution comes from the distribution of the walls on the second floor and the tributary area of every slab on the second floor. So the loads won't be the same in every one of the columns. So it might be the case that some columns will be exposed to a higher load than others. Now, with this kind of footing system, observe what happens when I apply a high load in this point. You can see that due to the stiffness that the transfer beams have, such load it's kind of transmitted to the neighbor footings, and the load is evenly spread over the terrain. The isolated footings that are very far from the higher load, just for saying something, and the footings that are not so rigidly connected as those one, experiment a kind of differential setting compared with this one. You can observe this in our 3D printed model, how it behaves. You can see that the soil in this area will be squeezed more than the soil in this area, and that's the idea of the of having such beams, such transfer beams with this depth. Now we have another footing systems in which the transfer beam is not as stiff as the one I designed for this house. This kind of systems is the most common here in Honduras, and because this one is more economic than this one. Now in this model, observe what happens when a higher load is located, for example, in this isolated footing. As you can see, the transfer beams have a lower stiffness compared with this one. So when higher load is concentrated on an isolated footing particularly, the footing settles in this location, and the transfer beam doesn't have the stiffness required to transfer the load to the neighboring footings. So the house will face a differential settlement, and that's a structural problem if that happens. So this system is kind of flexible. Now, using the same structural system, we are seeing a continuous footing. A continuous footing, it's a kind of footing system on which not all, but the most important, or at least the principal axes are supported by a kind of wall which might be made with concrete or reinforced masonry. This one is more stiffer than this one, but the price or the final cost of this footing is much more higher than this one. And you can see in this model, when I applied a higher load, for example, concentrated in a central region, the stiffness of all the system is transferred to the almost all the neighboring continuous footing, and the settlement of the house is expected to be nearly the same in all the area. You can see if I apply a higher load concentrated here, you can see how the weight is almost evenly distributed along all the footing system. So this kind of footing system is called continuous footing. A continuous footing looks something like this. Let me show you. This is a continuous footing. In Spanish we call it zapata corrida. And the idea is to put a kind of concrete wall or at least reinforced masonry wall behind the foundation beam, and then we have a footing system. And the other option of a continuous footing, it's a kind of wall, a kind of retaining wall made out of masonry, stone masonry, just below every foundation beam, as you can see here. So this kind of footing, it's called zapata corrida also, but it's made out of stone masonry. And as this one, the stiffness of this footing system is such that if a higher load is applied at some point, the system tries to distribute all the forces in all the neighboring footings. So we might expect no differential settlement with this kind of footing system, as you can see here. Or if we apply the higher load just around this corner, you can see that despite the settlements in this location is greater than this one, the whole system, as it acts, at least try to redistribute all forces evenly along all the systems. So what kind of element is this one? This one is like something like a distribution beam or tensor beam. This one as this one, and visualizing it on our 3D model, it will be this one. Actually, this beam does not have a structural function more than transfer some kind of stiffness for the isolated footing, and from the architectonic perspective, it serves just to divide different ground levels. For example, the parking garage that should be at 0, and in this area that we want to have a kind of slope, and that's the purpose for this structural system. And the same happens in the back of the house, which is this zone. In here we don't really have a wall over this area, over this beam, but it is there just to connect, or at least try to connect rigidly, the isolated footing in this region with this one. So you can see now how different footing systems behave under higher loads located in, for example, a particular location in the building.